Fair enough. Yeah. If it's shortest pass, then that makes it easier because I've done that one before.
How do you enter your audio?
Hello.
We got
We got
echo, I
act.
think.
Okay.
Zoom's not
All right.
Yeah.
Got it.
Oh, almost started. Oh, yeah. Oh, we had the HDMI button. There we go.
Ah, there it is. I'm still trying to find Chris Hunt.
Yes.
All right.
HDMI, HDMI. What's the other end of this cord go to?
There it is.
And then, yes. Oh, my precious minutes.
This one.
Yeah, I don't like that. I just trust the HDMI one more. It worked for a second. Or popping.
It is connecting. Your screen's showing that.
Yeah.
Try the other one.
Yeah. I think it's fuzzier though, I swear.
Yeah, it is a bit. Is this the right one connected?
Yeah, I just switched to HD. All right, let's reboot my laptop time.
Are you sure? Wait, hang on.
No.
You want to run on this laptop?
Good. I don't think there's any reason I need
Here, I can
Then we can at least get started.
yeah. All right. It's not sharing screen currently.
Yeah, you want to get this. You know how to set yourself. So much time thinking about timing. I don't even know what that is.
The projector is the problem.
That's not ideal. Oh, there we go. Something happened for a second.
Not good. The screen is not working for some reason.
But maybe it will in a second.
We're trying to figure this out.
Well, my computer's back up, so.
Yeah, if it's not.
Oh.
Ah! Ah! Huh?
Odd.
This sounds like it's the cable itself that's broken. That's not good.
Okay, let's try one more. I know that now that I know it's a cable, I have no faith this will work, but
Yeah.
okay, well there's two cables. So
In the meantime, might as well do announcements.
okay, sure, go for it. Well, I mess with this.
How's everyone doing? Doing well? Yeah. It's supposed to be rainy today, right? Yeah. Is it? Yeah. Thank you for coming out in class. Rain is all right, let's see what's coming up. We have lab 7 that's due Friday. Oh, and 2A is due today. How are people doing on 2A? Doing well? Doing badly? Few people. How many people think they're going to be able to get it done by tonight if they haven't finished? Sounds good. All right, that's where we want to be. Other than that, yeah, Lab 7 is going to be due this Friday. And then after that, we do have one more week before spring break. And at the very end of that week, we'll have both Lab 8 and Project 2 be due. So, a few things coming up. But we're about to finish this half of the semester soon.
I might have to do this on the chalkboard today. Huh? Okay, I'll try one more time with this one.
Yeah.
Weird that both of them are not working.
If it's not, yeah.
They're
What's a
restarting
single
the whole system.
what's a single source of point of failure then?
Right. What makes sense? This thing? I could turn this off and on again.
Yeah, so this is connected, right?
Yeah.
It is definitely seeing this.
Oh, okay. All right.
All right, we got this one to work.
Strange.
All right.
I'm not touching anything. I'm just gonna use your laptop because that's just what's happening today.
Yeah. All
All
right.
right, great. I don't think I need to touch
Yeah.
anything. All right, hi everybody.
Anything sensitive that song?
I'll try my best not to reveal your secrets.
Yeah, there's a non-zero chance there is, for example, an exam.
Right. Okay.
Like
Got it.
on here. That is
All right. Hi everybody. That was interesting. We tried two cables with two different laptops with two different inputs and restarted everything several times. Eventually this worked. So
Are you on the Zoom here?
I'm not on, but go ahead.
I'm gonna go.
Okay. So today we're going to be talking about priority queues. And I'm going to start by telling you about a new abstract data type you've never seen called a priority queue. A priority queue works like this. I'm going to take some things out of my backpack. Let's see. All right. Yeah, so there's four different operations. The first one is add. So I'm going to add some things to my bag. One is that thing. Another will be Dustin's hat. And the other will be this towel. Okay, so I put those three things in. I have three operations I could do. One of them is size. What will size give me? What number? 3, right? And what do you think remove smallest will give me if you saw the things? Justin's hat, right? Okay, so I remove the smallest. If I remove smallest again, I get my Bluetooth speaker. And if I remove smallest, I get the towel. Okay, that's a priority queue. That's all you really need to know. So what these are useful for is the idea of keeping track of the best thing so far, the smallest thing so far, the largest thing so far. We'll use this all over the place in this class. Okay, so let's see an example of why this data structure is useful. Why would we care about this bag where you can remove the smallest thing? Well, one of them is imagine we're trying to record a bunch of events in physics. We have particle detectors that are recording the energy of incoming particles, and we only want to record the m highest energy particles in a given day. So the naive thing to do, if you wanted to do this, is just create a list of every event you see. At the end of the day, you sort it using a particle energy comparator, and then you return the m particles with the highest energy for code that looks like this. So we have a detector. We want the m highest energy particles. And you'll notice what we do. We run a timer for a day, adding each particle. At the end, we sort all of the particles and then return only the first m. Yeah. Makes sense? Keep all the particles in a list. Give me only the biggest ones. This, however, can use a lot of memory because you may detect a whole lot of particles. So we want to do better than this, where instead of using as much memory as the number of particles all day, which will be n, that's the total number of particles, I want to use only m memory. That's going to be my goal. So I can do this by using what I will call a min PQ. The thing we just saw is a priority queue. Sorry, I didn't actually say it out loud earlier. This is a min PQ, a priority queue that gives you the minimum item. And so here, I want to do this in only m memory. So instead of storing maybe a trillion particles that come during the course of the day, if m is 20, I only want to think about the 20 highest energy particles at any given time. So I'd like you to think about that for a minute. How would that look? So I make this backpack, this priority queue, and I want to do this in m memory. How would I do that? I'll give you guys a minute or so to think about it. By the way, the fact that we got started late is fine. I'm just going to cut the last thing, and I'll tell you which video to watch later. Okay, thoughts. What should I do? A particle comes in, what do I do with it? Put it in the bag. Great. Okay, that seems clear. Then what? What's special? What else can we do? Remove immediately. We don't want I just add. Okay, so taking some particles. So as I'm adding particles, tell me when to stop. N. Why should I stop when I have n things? Because I only want to have n memory. So okay, so once I get to n items, say n is 20, I got 20 particles in the bag. What do I do now? Remove the smallest. And what do I do with it? Write it out. What should I do with this thing? Throw it away. We don't care about it. We only care about the n highest energy particles. So we're going to grab the particles, put them in the bag. As soon as we have 20 of them, so anytime we go above m, we're going to remove the smallest. Okay. So that's the algorithm you just came up with. Put each particle in the bag, removing them whenever we get too many. And then at the very end, we convert it into a list. Okay. This part's not very exciting. All right. This is a very common trick. So there's two things about this code I like. One, it is much more efficient than storing all trillion particles that might show up in a given day, because you only need to keep track of 20. And the other thing I like about it is that the code is actually, I mean, I don't know, it makes some intuitive sense. I think it's pretty. We don't have to explicitly compare the particles. The bag does that for us. Any questions about this? Okay, so this is the priority queue. There's many other problems this will be useful for. For example, if you want to do Google Map style directions, if you want to use an algorithm like Dijkstra's algorithm or A*, which we'll talk about later, a priority queue is the right tool. You'll be exploring a space, maintaining a list of all the things you could do next. Right? We'll talk about that later. Okay. So how would we build a priority queue? We know what it is as an abstract data type, but remember an abstract data type isn't an implementation. We need some actual implementation. There's a bunch of different things we could do. One possibility is that my bag secretly is an ordered array. In that case, get smallest is going to be really easy. You just get this item at the front of the list. But adding will be slow because every time you add a particle to the bag, you now need to get it into its exact place and potentially scoot all the items over. Same thing with remove smallest. When you remove the front item, now you need to shift everything over. You could maybe be a little more clever and speed this up in some ways, but it's not an actual tool. Another would be a bushy binary search tree. So in a binary search tree, if you have a bushy binary search tree, how do you find the smallest thing in a binary search tree? What do you do? Just keep going left, and then you'll get there. And once you run out of places to go left, you're done. That's going to be log n time. How do you add to a binary search tree? Well, you put it where it's supposed to go, and then you do some rotations in order to keep it balanced. And same with remove smallest. Okay. One issue is that if you have duplicate items, it's a little awkward because a binary search tree, as we described it, doesn't handle duplicates well. So you could just use 2-3 trees or LLRBs, and that would be fine. If you modify them to use duplicates, that would work fine. But I'm going to show you a way today that handles duplicates elegantly. What about a hash table? Adding to a hash table is fast, but if I want to find the smallest thing in a hash table, how do I do it? You got to go through everything. You don't know where the smallest thing is. There's no sense of ordering in a hash table. Okay. So we're going to see a new approach called a heap. Okay. You've never seen. Now, this particular data, actually, any questions about the bad implementations? Yeah.
Remove like when you're adding another item and the smallest that it is getting. So the next item that you're adding, n plus one, is basically comparing it to the smallest item and then checking whether it's smallest or
You know which data structure? Ordered array, bushy binary search tree, or hash
I'm
table?
just wondering generally about the structure of remove schedules.
Oh, how does remove smallest work? Yeah, it finds the smallest item. However, we don't know how, and then it removes it. So if it was a binary search tree, you would keep going left, get that item, and you know it's either 0 or 1 child, and then it'd be easy to remove. Yeah. My current priority queue does not have an iterable method, or it doesn't implement the iterable interface, but you certainly could. Yeah. Right. This is not a first in, first out. This is a any that I would just say it's best out first. How about that? Yeah.
Priority.
Yeah. Could you use some kind of increasing hash code function as a way to finagle a hash table into this? Not in any way that seems natural to me, because the point of hash table is that it should spread things out kind of randomly. So forcing order just seems contrary to that purpose. Someone's probably come up with some kind of clever thing that kind of does that, but I don't know. Yeah. The reason I said remove smallest in an ordered array is I'm imagining that index 0 is where the smallest item is, and then you shift everything over. You can optimize a bit, but it's still going to be messy. Like you could try and do some tricks like you did with ArrayDeck, which will help a bit, but still not going to get you where you want to be. But you're right. You could optimize remove smallest. All right. Let's talk about heaps then. So heaps are going to be a new fourth column here. That's not a hash table. It's not a binary search tree. And sorry, it's not any of these three things. It's a totally new thing. And it's going to be a tree, another type of tree. I'm just going to introduce this definition out of nowhere, and you're just going to have to trust me. Unlike the binary search tree, which we invented together from scratch, this one's a message from heaven. Okay. So as I said, binary search trees would work, but we don't have a nice way to handle duplicates, and heaps are just another nice, simpler idea that does handle duplicates. So a binary min heap is just going to be a binary tree, like any of our binary trees, and it's going to have two extra properties. Okay, it's not a search tree, by the way. This is not a binary search tree. There's no like small things on the left, big things on the right. This is just a plain old binary tree of stuff. Its first property is that it is complete. And the second is that it obeys the min heap property. So the min heap property, I'll tell you first because it's simpler to understand. It's that every node's key is less than or equal to both of its children's keys. And that's recursively true all the way down. Very similar to a binary search tree. In a binary search tree, all my smaller items are to my left, all my bigger items are to my right. With a heap, this heap property says everybody below me is equal or smaller. Okay. Then there's complete. Complete's a little bit awkward, but it basically says that every level of the tree is full except for the bottom level, which can be partially empty. And if the bottom level is partially empty, all the nodes need to be as far left as possible. I can only really explain that by example. So these first two here are both binary min heaps. You'll see that every level of both trees is full. They're complete. And you'll notice that for these, every item is less than or equal to both of its children. Okay. This tree right here, also a min heap, and it is also complete. Now you might say, well, it doesn't feel complete to me, like there's something missing. Well, complete, the definition that we use, and that is standard if you look on a textbook or on Wikipedia or whatever, it allows this. Because even though there's some items missing, they're at the bottom level, and all of the items in the bottom level are as far left as possible. This one, however, is incomplete because there's a gap in the middle. And then here we have this example, which lacks the min heap property. Why? 4 and 5. So 5 is bigger than 4, which is not allowed. Okay, so I'm going to have you do one rather than ask me questions. How many of these are min heaps? See if the definition makes sense. Here's what's on the tab. Croatia. Croatia. I was in Croatia. I know. Before Zella was born. The last trips, maybe. Japan was the last. That's fair. Yeah. Traveling was so easy. Yeah, before the kids. Oh, I don't. Okay. All right. The most popular answer is also the correct, but there's one that's tricking you guys a little bit. So it turns out that one of them is not a tree that many of you thought was. Sorry, one of them is not a heap, a min heap, and it's this one. This one's incomplete. And this is that fuzzy part of the completeness definition that's annoying. So here, not every level is full. I never really said what full meant. It must pain your heart a little that it's a little fuzzy. Oh, you're okay with it. But the top level has one item, the next level has two items, the next level has four, and so forth. This one's not complete because the second level is not as full as it could be. Okay. Now you know what completeness is from this counter example. Okay, any questions? Here's a fun secret. Somewhere in this room is my 7-year-old daughter who's homesick. So, just a fun fact. You won't find her. She's in the front with me and Justin. All right, anyway. Hiding. So, what good are heaps? Heaps lend themselves very naturally to a priority queue. So here's an easy question, hopefully. How would you do get smallest? What do you think? Yeah, it's the top one. It's the root. Get smallest there. All right. Let's talk about adding to a heap. So get smallest is easy. We just need size, add, get smallest, and remove smallest. So how would add work? So I'm gonna have you think about add. Okay. So I want you to figure out a way to insert 3 into this heap in a way that is log time. And I'll give you a hint. You should exploit the fact that what you already have is a min heap. It has completeness and it has the min heap property. I'll give you guys a minute or so to figure out how on earth do I put a 3 in here so that I end up with a correct min heap. On pacing. That makes no sense. Oh, I see why. What happened? I was trying to figure out how I was on pace again, but it's because I'm not on pace for the faster version I had in mind to do the end. Okay, that's fine. Happens. Yeah. I'll give you a hint. If you want the tree to be complete, there's only really one place you should put it. Like, where should the 3 go when you first put it in? Here? Because that maintains completeness.
Make sure you can be seen on something.
Oh, yeah. Okay, so once you get the 3 there, then what? All right, so when I insert 3, it makes sense to me to start from this position. But this is not a min heap, right? So what can we do to fix this? Repair our invariant. Yeah? Rotation I don't like because it changes the shape of the tree. I want it to be complete. So we got to do something else weirder. Yeah, go ahead. Switch. Okay, we'll swim is the word I'll use. So I'm going to take this 3 and swap it with the 5. So I'm going to swim up the hierarchy to my rightful place. I end up there. Am I done? Not quite, because there's still a problem. I'm smaller than 5. So what should I do next? Go up. Okay, I'm here. Is there any chance that I've made a mistake and I need to go back down this way? No, because 5 was here. And we know that whatever is down here is all smaller than 5. So we know that we can be greedy and just go up and there won't be anything wrong. Okay, this is my true place. Okay, another one, 5. So the next thing we insert, we'll go here. I should have asked you instead of just doing it. So I want to insert a 5. Where should it go? To the left of the 6. Then what should we do? Swim. Okay, we get there and? Right, we're done. Okay. All right, that's adding to a heap. Any questions about this process? Oh, yeah.
Yeah, the larger.
Larger. Sorry, I said the wrong word. Yeah, larger. Why do we not care about duplicates? Well, it works, right? You just have a bunch of same things. It's fine if you have a bunch of. Oh, why would you ever want that? Yeah. Maybe you have multiple particles that are the same energy. Or maybe each thing is not just a number, but it has something associated with it, like 5 cats and 5 horses or whatever. Then they're distinct, and the key is the number, and the value is something else. Yeah. How do you know where the end of the list is? We'll get there. Yeah, that's coming in a while. Yeah, it's a good question. Like, how did I know where it was in memory? And that's a good question. Yeah.
Valid. Heat, if it was the other way, so I guess the right branch with the left branch.
Right. If you take a heap and you just switch left and right children, it's still a heap. That's fine.
Well,
Yeah.
You lose completeness in some cases.
You might lose completeness, but I'm imagining like if you take, right. Yeah. All right. How about removing? How would that work? So imagine you want to remove smallest. The first question, who's the smallest? 1. So we got to get rid of the root. Okay, what should we do? Think about it for a minute. I'll give you a hint in about a minute. Let's say you're removing the root. I mean, you could remove this one, but that's too complicated. Let's remove this. Oh yeah, I do that. Oh yeah. Oh, they did. The word.
Fired CEO and
Right.
most recently fired person gets
Right. Yeah. Yeah, exactly.
let's see how you
Yeah, although I changed that analogy from saying assassinating the president to removing the president today.
deposing.
Yeah. Okay, first thought I have is if 1 is gone, you need to fill in that gap with something. What should you fill it in with so the tree remains complete? So if 1 just gets vaporized, what do you put there so the tree is complete? Okay, keep thinking. Just give me my trick. So if I vaporize the root, it's gone. And what we can do to maintain completeness is bring 6 and put it into the root. So, right, 1's getting eliminated, 6 says what's happening to me, and now you're in the root. Now, that might seem weird because this is one of the items in the bottom level, and those are the least qualified items in the hierarchy, right? They're the biggest numbers. But it makes sense. I mean, I can take this item and stick that in the root, and now 6 is there, but we have a problem, right? This is not the right item to be in the root. So we need to either promote the 3 or the 1. Okay. So which one makes sense? I've highlighted 1, but why was this the right choice? It's the smaller. If we put 3 up here, we'd run into a problem. 3 would be bigger than 1, and then we'd have to percolate our way. Well, shouldn't be using that term right after homework 2. But if 3 came up here, we'd have to do some other fixes. But as long as we just have 2 choices and we go down that route, we should be in good shape. Are we done? The purple line suggests otherwise. Who are we going to bring up? 3, right? There we go. Okay. Now if we delete 1, okay, you already saw what's going to happen, but what item is going to take over and be the new root temporarily? 5, okay. Oh. All right, and here we have 2 choices, and now it doesn't really matter. We're just going to break the tie arbitrarily. We won't run into trouble either way for sure, because if we go this way, we know that 3 is smaller than everything over here, and if we go this way, we know that 3 is smaller than everything down here. So either choice is safe. Okay, so now I pick the one on the left, and we end up with 5. And 5, in this case, doesn't descend further. Could we swap with this 5? Sure. Does it do anything? No. All right, any questions about delete? Yeah. Yeah, we have this again, this weird question of like, I can see with my eyes where it is, but how would I do this on a computer? Like the recursive code for this sounds really scary. And we'll have a nice solution soon. Don't worry. Yeah. Don't have another. Right. I'm going to summarize this real quick, which is what the operations are. So get smallest always returns the item in the root node. And then in terms of companies, the analogy that I've always used is when you add a new item, you place the new employee in the last position, And then you'll promote them as high as possible based on their ranking on that website that was on Berkeley Reddit that someone sent me today. And did you guys see this?
What?
It's like it pairs up students from Berkeley, and then you get to rank them on how good they are based on their awards and whatever else. It's very silly. So anyway,
Feels kind of.
yeah, it's whatever. But yeah, so you put a new person at the bottom of the company, and then they climb up as high as possible. And then remove smallest, what happens is you eliminate or depose the president of the company. And then you take the rightmost person in the company who is most likely the most recently hired person. So you just say, I know I just need somebody. You're at the end of the line. You're the boss now. And then you demote them repeatedly, always having the better successor take over.
Yeah, this is not a good corporate structure. Do not work for a company that does this.
Yeah, this is not an appropriate way to do business. This may or may not be happening right now with the United States government. I don't know what's happening.
No, we're gonna lose funding.
We're not gonna lose. It's okay. Elon and I are buddies, I guess. I've never met him. We're cool. I'm gonna not go there. All right. No, I'm not. Okay. Anyway. So this question comes up. How do we do this in Java? Right? If I get deported because of that, you guys will come to the meeting where they're like, don't deport Josh Hug for making a joke that was kind of vague. It's not cool. Okay. It's getting dangerous. So how do we do this in Java? How do we find where the items should go? Like how do you know where the root is versus the last, like how do you find the last item in the tree that's available? So this brings up a really interesting question, which is how are we even going to represent the tree? So I'm going to show you 5 different ways to represent a tree, and the 5th and final way will make that job trivial, finding the most recently inserted item or the last item in the bottom level. But the most natural way you would imagine that you would do this is what I'll call tree 1A. Tree 1A is basically what you imagine in your minds, which is that each node has a key, like a value, like W or 0 or 5. And then you have children, like hard links, left, middle, or right. So this is a trinary tree as opposed to a binary tree. And that's because I'm just trying to point out trees could be whatever. So if you did BST MATLAB, this is the approach you used. They were fixed width nodes. You have values and you have links to your children. Okay. What other possibilities are there? Well, I'll give you a couple of strange ones. One of them is to have a map where the children are actually an array of links. So in this case, each tree has an array of children. So here W, this is the key, and here is the link. This is the tree 1B, and then these are the 3 children. This is an array of link 3. What does this let you do that the other one did not let you do? Like between these two, yeah? Yeah, you could have a variable number of children. Okay. So that gives you some more flexibility. And the point is here simply to say that this is the abstract data type that we have in mind when we say tree. This is how we implement it in Java. Here's another way of implementing it in Java. There are yet stranger possibilities. This one comes from Paul Hilfinger, who taught this class for a long time. And I co-taught with him my first time here, which I guess I'll call a sibling tree. In this approach, each node has a link to its children, and then each child, like the first child, will have links to its siblings. So that's called a sibling tree, I guess. So what will I call the first child? This is the favored child. Hey, Zella, we're talking about sibling stuff here. So in our tree, I'm not going to pick who's X and who's Y in my family. That's not appropriate, but I'm W. I have 2 kids, so I'll either point at Zella or Ilsia, and then Zella will point at her sister if she's X. Okay. And the key point is that all of these things could work. Like you could implement a tree using any of these 3 architectures, and anything you want to know, you could find using some code. Oh, see you guys. They're off to tell Elon. Future Doge members. They're ready to. They can't take the heat. All right. Anyway.
Oh, this is child.
Yeah.
That's a favorite child.
I think favorite child's more fun. Yeah.
No, you don't have favorites.
I don't have favorites, but you know,
You have
it's spicier. Okay. All right. So all 3 of these are approaches you could use to implement a tree. Right? Fixed width, variable width, sibling tree. Any questions about these three approaches? Okay. All right. What do we do with a heap? None of them. All right. I'm going to tell you some other weirder ideas. Okay. Another approach would be we've done this before too. This is what we did with disjoint sets. Another way to represent a tree is to store all of your keys in one array and then all of your parent information in another array. I mean, it's similar to what we did to disjoint sets. So if I have, for example, W, X, Y, and Z, I'm going to say that all of them have parent 0. And if you have an item that's its own parent, that just means, well, you're a root. And similarly here, this one's hard to understand because it's too simple. So here's an alternate tree. If I have a root K, a left E, a right V, a left B, and so forth, one way I could represent this tree is as an array of keys. Here they are. And then here's just all the parent links. So 0, 0, 0, 1, 1, 2, 2, 3, 3, whatever. So for example, item 12, what letter is in box 12 or is in node position 12? R. And who's its parent? V, which you can see over here. I say R or P, sorry, P. How do you know from this parents array who 12's parent is?
5.
Just look at that index, it's 5. And then what the element 5 is P. So even if I were to hide this slide here, like imagine that, or this part of the slide, imagine I crossed out this tree. You could redraw it from keys and parents, right? That's the key idea. And if you can do that, then you can write code that walks this tree. Yeah.
Shouldn't the parent of the root node be like negative?
You could also call this -1. I just use 0. Either one would be an appropriate way to just some exceptional value, right?
Or minus the size, it doesn't matter.
Right. So that's approach 2. And then approach 3 is going to be a slightly different approach. This right here, what do you notice about the structure of this parents array? It's like very regular. It's just 0, 0. Well, it's basically, who cares? 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And we don't really need it, right? Or we don't really need it to represent this type of tree. What's special about this tree? It's complete. So if your tree is complete, you don't need to store the structure, right? It's irrelevant. You know what the structure is just on the number of items. In other words, there's a one-to-one mapping between just knowing what the items are and the structure of the tree. That's almost a mathematically correct statement, okay? So this will only work for complete trees because a complete tree is a specific structure. So if you know the tree a priori is complete, then you just need the keys. And this is what we're going to do, right? So the way we store our priority queue, or our heap, I should say, is as a list of keys. And the reason it works is because we know that the heap is complete. And since it's complete, we don't need to store the structure explicitly. This is the entire tree. Kind of cool, right? It's just an array of things, but it's still a tree. What is the last item? Like if we were to delete the smallest, what item are we going to promote to the root? Well, from this diagram, what is it? X. And where is it here? 13, X, right? So all you need to do is look at element size, and that's the smallest. Or sorry, that's the new root. Okay. So that question of how do you find what to put in the root? Well, it's just the last item in the array that's active. Okay. Any questions about this? Very clever. Yeah.
After like the parent-child structure.
Well, so the parent-child structure is implicit. So I'm going to have you think about that in a moment. Before I do that, I'm going to tell you a slightly different version. Oh, no, actually, I'm going to do it right now. So you said I haven't captured the parent relationship, but I claim actually I have. So this is the code for swim, right? How does it work? If the parent key is bigger than the current key that I'm swimming, then I'm going to swap with the parent, and then I will swim that whoever the parent is. So that's just an index. So what's the parent method look like? How do you know the parent? If I am number 14, what number is my parent? Think about that for about a minute. So just to run this down real quick, who's 12's parent? 5. Who's 5's parent? 2. Who's 2's parent? 0. That's what you're trying to write. Think again for about 30 more seconds. I'll tell you what I came up with. Okay. So we need a function that if we take 12, we get 5, and we also take 11, we get 5. What I came up with is you just subtract 1 and then divide by 2, and it turns out Java will just truncate. Okay. So 12 minus 1 is 11. 11 divided by 2 is 5.5. Java rounds down. Okay. Maybe you didn't know that, but that's what it does. Okay. So the parent function works. And you'll notice I didn't explicitly represent the tree structure anywhere. I just know, like that is the tree structure. The parent is always whatever integer you're at, minus 1 divided by 2. You could write the similar question about left child and right child. It's a very similar, just the inverse of this. Any questions about this? This is pretty deep. Like this is pretty close to the actual code for writing a heap. I just need to write a swap function, which is going to be pretty simple. This is going to swap 2 elements of an array. I'm going to wait for any question. So notably, this is the entire data structure. This is where you put your stuff. The memory boxes for your heap are right here. It's an array of keys. There's no links, just an array of keys. There's no dot left, no dot right. It's just this. Yeah. What happens if you pass in 0? We get 0, minus 1, minus 1. It's just itself. Yeah. Seems okay, I guess.
Minus 1 over 2 does end up getting to 0, I think.
Yeah, minus 1 over 2 is 0. I'm pretty
It
sure.
doesn't round down, it rounds to 0.
Yeah, it truncates. Yeah, right. Sorry, I might have said round down. I meant truncate. Yeah.
Right?
It works if the tree is complete, right? So if we're adding and taking things away, we maintain completeness. So the algorithm that you guys came up with some help from me always maintains completeness. Heaps must be complete for this code to work. So a lot of stuff balanced against each other with this data structure that's very nice. Like the completeness makes it possible to store it as an array, which saves you a ton of memory and makes your code very simple. It's very pretty. Okay. All right. So that's all of the different tree representations we talked about. We have these 3 that we could do that are explicit links. We can have keys and parents, but this one's a little redundant. I mean, it's completely redundant in the case of a complete tree. I should have said completely. And then lastly, array of keys is the simplest. By the way, when you're watching any instructor, I encourage you to listen for how many times people say it's kind of redundant, or like there's this part where instructors couch their words occasionally when they shouldn't because they're afraid of making a tiny mistake, which is I think what I just did. So listen to all the like smartest people you've ever heard speak. See when they do that annoying thing when they don't just state it seriously. Okay. Hopefully I haven't ruined future lectures of my own or Justin's or whoever else. All right. All right. And then I'll mention this, which is the Princeton textbook implementation, which is to leave 1 empty slot. So in the Princeton textbook, they leave the left slot open. And the reason they do that is that makes the math slightly nicer. And so instead of parent being k minus 1 over 2, it's just k over 2. So if you see this in any old exams in this class or old worksheets or maybe current worksheets, I don't remember if we do this right now. I haven't looked at it one. We do this. Okay, so the worksheet does this. It's a little nicer. Are you wasting 1 key's worth of space? Sure.
Not working.
Yeah. Okay. So let me summarize this whole thing. We just had a new column of ways to implement a priority queue. It had an add and a remove smallest method that are log in because you only need to do either in swims or in sinks, and you have get smallest, which is just the root. The reason that's better than a binary search tree is that items of the same priority are hard to handle. So there's a bunch of questions you might have, like why is it called a priority queue? Well, it's a queue where the position or the order in which things come out is its priority. The heap, I should note, is not actually log in. It's log in amortized because it's an array. And so what happens when your array gets too big? you got to resize it. So technically it's not log n, it's log n on an amortized basis. You can make a constant get smallest operation, which I do. BSTs. They can have a constant get smallest. If you just keep a pointer to smallest, just fun little point. As I noted, heaps can handle duplicates more easily, and array-based heaps take a lot less memory. So if you use a array-based heap, it's about a third the memory you need compared to 1A. Okay. There's some implementation questions you might ask, like how do you know which item in a priority queue is larger? We would need to change this a little bit. So what would I need to change in order to know that there exists a default comparison? Here it's just item. What could we do? Yeah? Yeah, we could say item. I think it's actually extends comparable, though I don't remember the syntax well. What constructor would we need to allow multiple orderings? So you create a priority queue and you want to be able to sort on an arbitrary order. What does the constructor need to take as an argument? A comparator, right? Oh yeah, I got one more thing, which is a summary of data structures. Now this is the part, since we had a 5-minute delay, I'm actually not going to be able to build the thing live that I wanted to do, but I just want to summarize what we've done with data structures so far and to tee up the last couple we're going to do. What we've been solving for the last few weeks is what's called the search problem. Given you have a stream of data coming at you, you want to get information of interest. So websites are posting to their Friendster page. I intentionally picked something well before I taught anything. And you want to only serve content to friends. It's a retrieval process, and it's very important to get right and efficient. Or likewise, we have a bunch of weather stations, and we want to show the weather map for a specific date and time. There are 5 different abstract data types we've talked about that all solve the search problem in different ways. So in a list, the way you store thing in a list is you can add an item, or you can actually insert into a specific location. It's a list, very, very intuitive. And you can get items back by index. Maps or sets and maps are a little bit different. With sets, you can add items, but whenever you want to retrieve, you don't have a notion of like where it is. You just want to know, is the item in the list or in the set at all? So you search by key identity, and maps are just the same. What's the difference between a set and a map? A set always gives you back true or false, and a map gives you values, right? A priority queue is a bit different. You add keys, but in this case, instead of checking if it's the small or instead of checking if it exists or getting the corresponding value, here what we're retrieving is the smallest item. And you can think of the thing we're retrieving by is key order or key size, right? And then there's disjoint sets, which was a little more complicated, but there we store something by storing connections, and then we retrieve using isConnected. Okay, so all 5 of these are different ways of implementing or solving some kind of search problem. This is the part where if we'd had 5 more minutes that I wasn't fumbling around with the projector, we could have done. Instead, I will show you the pre-cooked version from a previous semester, which is to say that each of these abstract data types, they have a bunch of potential implementations. What just happened?
Why is that one all over?
Okay, I fixed it. I don't know what happened. All right. Okay. So each of these, like a set and a map, there's lots of ways to do it. We can have a chaining hash table, which we talked about in class, a linear probing hash table, which we did not. But you could also implement a set or a map as an array or a linked list, but I have them red. Why? What do you think? Inefficient, right? Sets and maps, binary search trees, also not efficient, but red, black, and B trees, those are efficient. Could we use the heap to implement those? Sure, but it wouldn't be very fast. If I wanted to do get for a map with a heap, you have to look over the whole heap. Likewise for the priority queue. There's many ways of doing it, some that are good, some that are bad. This is something a student which suggested. I made it dark red because it's too weird. Okay? All right. Like using a hash table to do a priority queue. It just seems like dirty in a million ways. And this abstraction happens in layers. Like in a priority queue, I said that one way to do it is a heap ordered tree. But a heap ordered tree, how do you represent that? Well, we saw 6 different ways of implementing a heap ordered tree. Or in a hash table, each bucket could be whatever. It could be, like Justin showed, a linked list, but each bucket could also be a binary search tree. And in the case of Java, sometimes it uses a linked list, and sometimes it uses a search tree, if it's worried about imbalance. And then there's also a bunch of specialized data structures. Like there's sub data types of lists, stacks, queues, and decks. In that case, a linked list and a resizing array are perfectly lovely, and so forth. Anyway, so there is a video online in which I'll spend, instead of just these 5 minutes, more like 11 talking about this. So if you'd like, I encourage you to check out that video. So data structures, I'll just say at the end, they're a way of organizing data. And if you go to the Wikipedia article for data structure, you'll see you've learned lots of these. We will do 2 more in class, tries and graphs. Thank you, everybody. Sorry about the AV issues. Okay, I gotta go. I gotta go to another meeting, like instantly.
Okay.
Thank you for being.
Sorry, you have to go to meetings all day.
Yeah, it's time. The next one will be fun. The next one, actually, you can't come. So I actually have to put you in a room next to me.
All right. Right.
Yeah. And you'll get the recording up. Oh, yeah, I should take my laptop.
Probably.
Yeah. Yeah. Let's see. Yeah. I will send you the email link to submit the letter of recommendation.
Yes.
Is that how's that?
It's good. I mean, you sent the exact what I need.
Great.
You know what?